Hi, in this particular video, we'll be talking about Fibonacci numbers. So Fibonacci number series is generated using this base cases of f of 0 to be 0 and f of 1 to be 1, and using this recurrence relation quite famously known as f of n to be equal to f of n minus 1 plus f of n minus 2. That is the sum of the previous two terms. Okay, so if you look at the Fibonacci series, this is 0, 1, 1, 2, 3, 5, 8, 13, 21 and so on, right? So if you just add these two terms, you get the next term, right? That's how Fibonacci numbers are generated. Now, let's quickly talk about Fibonacci numbers use cases and different relations by which you can calculate them, and what are the different use cases that are frequently asked in competitive programming. Okay, so let's say Fibonacci number is a recurrence relation of this form, f of n equal to f of n minus 1 plus f of n minus 2. So this is a second order equation, to be precise, recurrence relation, and using generating function techniques, if we try to solve this particular formula, we get this particular relation, which is also known as Binet's formula, that 1 by root 5 multiplied by 1 plus root 5 by 2 minus 1 by root 5, 1 minus root 5 by 2 whole to the power n on both sides, right? So this particular formula is like a closed form term to get nth Fibonacci number. However, these contain these irrational terms, and that really makes it difficult to calculate in actual computers precisely. Okay, so even though these are the Fibonacci numbers are integer, if you try to put them in a float and put the value of root 5 and all, you will not get the correct value. Okay, so that's why this particular relation is not directly used to calculate Fibonacci values. However, if you are trying to find out some nth number in a notebook and you want to find out a good approximation, this term on the end is, this particular part is less than 1, right? So 1 minus root 5 is less by 2 is less than 1. So this particular term diminishes very fast. So this is like a quick approximation that you can take for nth term of Fibonacci number. Okay, this particular 1 plus root 5 by 2 is also called golden ratio, and based on that, this is the particular formula in golden ratios term. Okay. Now Fibonacci numbers can also be found using a relation of matrices, that okay, if you have this matrix 1 1 1 0 equal to f of n, f equal to f of n plus 1, f of n, f of n, f of n minus 1, if we just raise this to the power n. Okay, now why this happens is because this particular relation holds true over here, that if it's f of n minus 1, and then you add these two values. So when you multiply this particular vector over here with this particular row over here, you get f of n plus 1, right? That is the recurrence relation that is being used over here. And if you multiply this particular vector with this particular row, you get f of n only, because 0 multiplied f of n minus 1 gets removed. So this is how you like move from f of n minus 1 to f of n plus 1 f of n, right? Using by multiplying this particular matrix. So this is a special matrix that can help you to find out any Fibonacci number. Okay, so we will look at the ways to computation of Fibonacci number next. So the first one is a very simple iterative way, that if you need Fibonacci numbers up to, let's say, n is less than or equal to 10 to the power 6, and you need to calculate all the Fibonacci numbers, you can use something like just create an array of 10 to the power 6 and initialize the first two values with zeros and ones, and then like use this recurrence relation to build up this. So just add the previous two values to get this, right? So this is pretty simple to do, and this would be handled very efficiently in the code. So you can find this Fibonacci values easily for large numbers with taking mods and all. Okay, so this works with the case where n is up to 10 to the power 6. Makes sense? Now if say you need to find Fibonacci number mod some value, mod some m up to, let's say, n is less than or equal to 10 to the power very large number, let's say up to 10 to the power 18, because that fits in long. So if you want to find it for such large n, what we can use is this particular relation that we defined 2 slides back, which is 1 1 1 0 to the power n will be equal to this particular matrix. So from this, if we take this matrix and take it to the power n, we can get the f of n at this particular location of the matrix, right? So this 2 cross 2 matrix will remain 2 cross 2 even after you multiply them n number of times. So you can get the f of n from this particular position in the matrix, right? And to find out some matrix x, let's say, to the power n, we can simply use the binary exponentiation technique that we discussed for numbers, because for binary exponentiation you just need two operators to be defined, right? Something called multiply and modulo, right? These are the only two operators that we were using. And one more thing, we were also using addition. so addition is not required in this particular format, but even if you need addition, that's also okay. Okay, so if these are the three things that are being required in exponentiation, any particular type of number or structure, if these are the three things that are being required in any type of structure to be propagated through binary exponentiation, if you want to find to the power n for a structure which has these operators defined, then you can find them fairly easily using binary exponentiation technique, because you just replace all these operations for that particular object. So over here the structure we are talking about is the matrix. So for matrix we know that multiplication is defined, we know addition is defined, we know modulo is defined. So when we take modulo, we take each of the individual terms modulo, right? So that's how we define modulo for matrices. So if these three operations are defined for any structure, then we can use exponentiation techniques. So it might be binary exponentiation to calculate n, to multiply, and there are a lot of different exponentiation techniques. But if we want to find the binary exponentiation idea for any particular structure, if these are there, we are good to go. So similarly for matrix, you just replace the matrix, the long or integers that you have in the function with the matrix, it will work provided the operations are defined correctly, right? So we can find then any Fibonacci number for any nth Fibonacci number in order log n, because this will take us order log n. Why? Because this particular is a 2 by 2 matrix, right? So all these operations that we have over here are like order 1 only, because there are like maybe 4 or 8 number of operations to be done in these cases, right? So there is like these operations are order 1. So we know that binary exponentiation takes log n number of steps, and hence the complexity for this would be order log n. Okay. Now we'll talk about some properties of Fibonacci number that you should keep in mind while solving problems, because in some problems you might require these identities. So first one is sum of Fibonacci numbers, that is from 0 to n. If you add up the Fibonacci numbers, these come out to be f of n plus 2 minus 1. So you don't need to remember the proofs of these. However, let me quickly illustrate the proof of this one, because it's simple to do. For some of the relations it's pretty difficult, and you need to use inductions and other things to prove the relation. Okay. So what we can do is, let's say this goes up to f of n. So what you can do is, let's keep two terms at the end. So what you can do is you can add, let's say you can add f of 1, okay, into this, and you subtract f of 1 from answer. Okay. So if we add f of 1, these two get added and this makes f of 2, right? Then these two gets added and this makes f of 3. So this is using the recurrence relation of Fibonacci numbers. Okay. Now these two gets added and so on. So finally you get something over here, then these two gets added, this gives f of n plus 1, and then these two gets added and this gives f of n plus 2. Okay, and then remember we added f of 1 out of nowhere, so we have to subtract that, so that f of 1 is nothing but 1, so that's why we subtract 1 from this. Okay, and that's how we get this particular relation. Okay, now let's say if you want to find out the sum of squares, so sum of squares of Fibonacci numbers is defined to be f of n multiplied by f of n plus 1. Okay, if you take it up to n, this is the formula. So we'll not be going into the proofs of these particular formulas. However, these are some things you should know, that okay, I can find out this, and then if you need in some particular problem, you can just quickly Google them up. Okay. Now there is another something called convolution property of Fibonacci numbers, and this is sometimes useful in some specific problems. Now at times the problem might disguise you with this particular expression on one of the sides, and then you need to understand, okay, this is nothing but f of n. Okay, so f of n is always equal to f of for some any m, f of m multiplied by f of n minus m plus 1 plus f of m minus 1 f of n minus m, right? This is a convolution property of Fibonacci numbers. Okay, so in case you see some term like this, you need to know that okay, this is nothing but f of n. Okay. Now there is one nice property of Fibonacci number, that any Fibonacci number n divides any multiple, any Fibonacci number at the index which is multiple of n. Okay. Now, or conversely, you can also say that if Fibonacci number n divides Fibonacci number n, then you can say that n divides m provided n is greater than 2. Right? This holds true. So this is something you can keep in mind, because this is a very nice property of Fibonacci numbers when you need to find out divisibility of numbers on all. Also, there is a very interesting property of Fibonacci number which is regarding GCD of Fibonacci numbers, that when you need to find out GCD of two Fibonacci number f of n and f of m, you can take the GCD into the indexes. So Fibonacci number f n and m's GCD would be Fibonacci number of GCD of n, right? and this really makes it easy to find out Fibonacci number, GCD of large Fibonacci number, because you cannot really find out the large numbers and then take a GCD, because then you will have to store them in modular, right? So instead what you can do is you can calculate the GCD first and then take the Fibonacci, and that would be correct. Okay. So even if, let's say, you are given two numbers, find out f of 100 and f of 200 GCD, you can easily find out. So you know that the answer for this would be nothing but f of 100 and 200, right? The GCD of these two numbers. So this you can find out as to be 100, and you can find out f of 100 mod some number. But however, by calculating GCD by calculating individual numbers first and then taking GCD is very difficult. Okay? So this property is specifically used a lot in some of the questions where you have to find GCD, of course. Okay? So these are some of the most important properties. There are few more as well, but however, we'll be restricting ourselves to only these properties. Okay? So that's all for this video. Thank you, and see you in the next one.